диплом лауреата премии 2012 года Хуану Малдасене. So I would like to
Well, thank you very much. It's a pleasure to be here at this great institution with its great tradition in physics, theoretical physics. And well, thank you for this prize. It's a great honor to receive this prize, the Pomerancuk prize. We always learn about the history of string theory and how the Pomeran was so important in the history of string theory. So it's especially an honor for me having worked in string theory for so long. So I'm going to give a talk about this relationship between string theory and gravity. And this is a relationship between quantum field theories on one hand, and so quantum field theories on one hand and gravity on the other hand. So the relationship is such that we have the quantum field theory on the boundary of some space-time is going to be equal to gravity in the interior of that space-time. The gravity theories are, the relationship is a quantum mechanical relationship. So here we have quantum field theories such as gauge theories or similar to QCD. And here we have quantum gravity theories defined by string theory. So the plan of this talk is just to review some things about QCD strings and the Larsen limit, the limit of a large number of colors. And then we'll see an example for supersymmetric QCD and how it leads to a gravitational theory in 10 dimensions, and then how that is related to black holes. Now in the 60s, when many new particles were discovered, strongly interacting particles were discovered, it was thought that perhaps they could be viewed as different oscillation modes of a string. And the motivation for this was mainly phenomenological, because the spectrum of meson resonances, these are the data of the masses and spins of, these are the square of the masses, and these are the spins of various mesons. And they lie in a straight line, and that straight line can be understood from a rotating string model, where you have a relativistic string, and then the angular momentum and the mass are related by a linear relation like this with the tension of the string. Now later, experiments at higher energies revealed that really these hadrons are made with quarks and gluons. And so quarks have a new property which is called color, and it's a new gauge symmetry similar to the gauge symmetry of electromagnetism. So in this way similar to how the electron interacts with other electrons exchanging photons, here the quarks interact with other quarks exchanging gluons. Gluons have a color and an anti-color. Quarks have a single color that changes when you have such an interaction. New feature is that gluons can interact with each other, and one of the consequences of this interaction is that the coupling constant becomes smaller and smaller at high energies. And for this reason, QCD is easier to study at high energies, and this is the reason why you had to do experiments at high energies to really see the constituents, the hadrons, the quarks and gluons. But this same feature makes it harder to study at low energies, and at low energies we expect to see confinement. So the idea that if you create a quark and an anti-quark, the color electric field lines sort of interact with each other and form narrow tubes as opposed to dispersing throughout space as they do in electromagnetism. And these narrow tubes then have a constant energy per unit length. So as you separate them more and more, you create more and more of this tube. You get a potential which is proportional to the energy density of the tube, which is like the tension of the string, times the length. So at low energies we have something that looks like a string, and indeed the hadron spectrum has features that reveal this, that can be explained in terms of the string. And this string picture is also used in phenomenology in the Bloom model, for example, some models of patternization. So one question is, how do these strings emerge in QCD, and whether we can have an effective low energy theory in terms of strings. One path to strings is the Larsen limit. So if instead the strings emerge most clearly if you take a theory with a large number of colors instead of 3 colors. And then in that case, you have each gluon has a color and an anticolor. I represented them here by these 2 dots. And in such a situation, so if the color of one gluon is correlated with the anticolor of the next, and here I drew the color and anticolor with the same color. If they are correlated, then the interaction would be relatively strong, would be proportional to g squared, and that would be the effective interaction when the colors are correlated. While if the colors are not correlated, then they interact much more weakly. So they are suppressed by 1/n. Because it's very improbable that this color is similar to this one. But we saw in the previous transparency that the colors had to be correlated in order to get an exchange contribute. So this form kind of necklaces, gluons which are color correlated, form an object which looks a bit like a string. So this picture, the mesons with the open strings, so they have a quark and then a bunch of gluons and another quark, and the closed strings are the objects called gluons. Now this is a qualitative picture, and it's valid for any gauge theory, not just QCD, but not the Larsen limit of QCD, but any gauge theory based on an SUN gauge group. For any such theory, this argument suggests that we should have a kind of string. It doesn't even need to be a 4-dimensional gauge theory. It could be a 3-dimensional gauge theory. It could be a 0-dimensional gauge theory. That is to say, it could be a matrix integral. And this argument still suggests the existence of some kind of string. But it doesn't tell you, unfortunately, this argument doesn't tell you exactly how to find this string. So, if we are interested in QCD, one would imagine first understanding the theory with any but infinity, and that should be a free string theory, so a string where the strings do not interact with each other, and then doing the expansion in 1/n would be taking into account the string interactions, and then setting n equal to 3 in that expansion would be trying to get an approximation to QCD. So from now on, I'm going to well, let's first concentrate on the n equal to infinity case. It's supposed to be some string theory, and the previous argument suggested it's some string theory, but it would be nice to guess exactly what the string theory is. And when trying to guess that string theory, 2 problems were encountered. One was that the simplest action that you could postulate for the string, which is just the area that the string sweeps as it moves in space-time, leads to a theory that when you quantize it, it's not consistent in 4 dimensions. But it is consistent in 26 dimensions. So when people realized this, they started studying this string theory in 26 dimensions. However, if for the purpose of chromodynamics or describing a 4-dimensional gauge theory, you would like to have you would have thought that the string is moving 4 dimensions, but you find that you need at least 1 more dimension. And you can think of this 1 more dimension as the thickness of the string. So you need 1 more variable to describe the string. You cannot take it infinitely thin, to be infinitely thin. You can have some thickness. That was one issue. And the other issue is that the string theories that were understood, like this 26-dimensional string theory, always contain a state with mass equal to 0 and spin 2, which is a gravity. But in QCD, there are no massless particles, but furthermore, the graviton has the interactions of gravity, not of strong interactions. And for this reason, usually string theories are commonly used to study quantum gravity. So when these people realized that string theories predict gravity, they said, well, let's forget about string theory for strong interactions and consider string theory to study quantum gravity. However, we still have the strings in QCD, and the question is what kind of strings describe QCD. And so we'll combine these 2 problems into a solution. So the idea is to look not for a string that moves in 4 dimensions, but a string that moves in 5 dimensions. And the 5-dimensional theory is the one that has gravity, but not the 4-dimensional theory. So the idea is that we have a 5-dimensional space. It will be a curved space. This curvature well, has various manifestations, and one of them is that there will be a gravitational potential in the extra dimension, which has a certain minimum. And so now the graviton, which was massless in 5 dimensions, due to the confining effect of this gravitational potential, the fact that it cannot move in this extra dimension and the wave function has to decrease in these two directions, implies that the graviton will have some non-zero kinetic energy in the extra dimension, and that will give it a mass from the 4-dimensional point of view. So in this way, we can reconcile the fact that string theories in general have gravity with the massless particles, with the fact that in QCD we don't expect to have massless particles. So now, in principle, so that's a cartoon of what we would like to find, and but we would have to find this 5-dimensional geometry. And in principle, we should solve the equations of string theory, which are a kind of extension of Einstein's equations, and they're very difficult to solve. They're expressed in terms of 2-dimensional conformal field theories. So we consider a simpler case first, so a case with more symmetry, and the symmetries will allow us to say what the space-time is. So we look at a version of QCD with more symmetries. And that version of QCD with more symmetries is this theory, which we can call most supersymmetric QCD, sometimes also called n equal to 4 superior mills. This n is not the number of colors, but the number of supersymmetries. And well, it has this feature called supersymmetry, symmetry that relates positive fermions. It has many supersymmetries. And supersymmetry could be a symmetry of the real world. For that purpose, it's useful to study these theories. But really, we study it because it is a simpler case. Now, it's very similar in spirit to QCD, but it has an important difference, which is important for what we're going to say, which is that this most supersymmetric QCD is actually scale invariant. Now, classical electromagnetism is scale invariant, and QCD is also scale invariant classically, but quantum mechanically we saw that the coupling depended on the energy. But this theory that we're considering right now is scale invariant even when you take quantum mechanical effects into account. So it has a bigger symmetry group, which in particular contains scale transformations, and these importantly, these scale transformations constrain the shape of this 5-dimensional spacetime. So any 5-dimensional spacetime can be written, that has of course Poincare symmetry, can be written as the usual Minkowski space plus the extra dimension. We can set the coefficient by 1 by choosing this coordinate appropriately. And then if we demand that when x goes to lambda x, this metric is invariant, then we find that c should also go to lambda c, and this factor in front should be 1 over c. And then this metric is invariant under these three scalings. So the scalings are just an isometry of this metric. Now this factor in front has various names. We can call it the redshift factor because it relates the coordinate time here, which is the time measured in the gauge theory, with the proper time. Sometimes called warp factor. Warp factor is the same as redshift factor, multiplies of dimensions. But we can more physically think of it as a kind of gravitational potential. So this is again the final form of space-time, has some radius of curvature, and we sometimes draw it as a picture this way. So we have the 4-dimensional slices and the extra coordinate. And in the extra coordinate, we have a gravitational potential which becomes very large at c equal to 0. So massive particles cannot. You have a massive particle coming from this side, it cannot go all the way to c equal to 0. In fact, the proper spatial distance of c equal to 0 is infinite. This gravitational potential doesn't have a minimum. Really, a particle can go here to the right, and it can move to the right, and that is related to the fact that this theory is scale invariant. A few words about anti-Sitter space. So this space that we just found, whose metric was in this previous transparency, is called anti-Sitter space. And it's a closed Cassey to hyperbolic space. So it's a space which has constant negative curvature, and it's really the Lorentzian version of hyperbolic space. The anti comes from the fact that this person called De Sitter found a solution with positive cosmological constant. So, and anti means that it has negative cosmological constant. So the De Sitter space is more relevant for cosmology because it describes accelerated expanding universes. This one, anti-De Sitter, is more relevant for describing duals of gauge theories. This is another nice picture. Hyperbolic space. There's a lot of room in hyperbolic space. As you go move in the radial direction, the area grows fast away. This is a picture now of the Lorentzian version, so the spatial cross-sections are hyperbolic space. Massive particle, so it has a boundary at infinity, which in the previous transparencies I was writing this as R4, but it could also be viewed as S3 times R. And massive particle cannot get all the way to the boundary, it's just reflected from the boundary by the gravitational potential. Light rays can go to the boundary and back if you put some reflecting boundary conditions. And the time it takes to do this is of the order of the radius of curvature. So you should think of anti-De Sitter space as a kind of gravitational box of size roughly R. Because that's the time it takes for particles to come back when you send them away. So you shouldn't shoot the gun in anti-De Sitter space. It will come back to you. You can also think of so then, now there is a relationship between, we said there is a relationship between the gauge theory that lives in 4 dimensions and the gravity theory that lives in 5 dimensions. And there is a dictionary that tells us how to relate the quantities we compute in 5 dimensions to the quantities we compute in 4 dimensions. And a general entry in this dictionary is the relationship between the gravity in the bulk and the stress tensor operator in the boundary theory. So any quantum field theory will have a stress tensor operator. We can calculate correlation functions of the stress tensor, so we measure the energy density at one point. X is a 4-dimensional point, Y is another 4-dimensional point, etc. And this is a quantity we can calculate in the quantum field theory. We can calculate it using Feynman diagrams or the lattice or however we want to compute it. And this quantity is supposed to be equal to the probability amplitude that gravitons go between these different points on the boundary. So X, Y, and Z are 3 points on the boundary. We have gravitational waves that are emitted from this point and interact in the interior according to the laws of essentially Einstein gravity, or more generally string theory. And these interactions determine the stress tensor correlators. And in this way, so this is one particular entry of the dictionary, and we can have other fields in the interior or other particles in the interior. They are related to other operators. So instead of the stress tensor, other operators of the theory. There is a relationship between the scaling dimension of the operator and the mass of the particle in the bulk, which is given by this formula. So you can check that when the mass is 0, as is the case for gravity, then the dimension is 4, which is the correct dimension for energy density. It has dimensions of 1 over length to the 4th power. Now, going back to this more supersymmetric UCD version, so we expected to have a string theory in anti-De Sitter 5, but it also has a bunch of symmetries, and we remarked on the fact that it has supersymmetry. And it has the same amount of supersymmetry as 10-dimensional superstring theory. Now, given that we added 1 more dimension, it's not a very big logical step to add 5 more. And we can say that perhaps it's related to 10-dimensional superstring theory and 5-dimensional anti-De Sitter times other thing which is 5-dimensional. And the simplest possibility that has the right symmetries is a 5-sphere. So in fact, this space is a solution of string theory, and it's a solution which contains a magnetic field on the S5. It's very similar to extremal black hole solutions in 4 dimensions, which contain magnetic fields on the sphere. So this is something similar. And this magnetic field is quantized, and so the integral of the magnetic field is some integer number. Now, before I continue, I would like to open small parentheses and say a few things about string theories for those of you who are not familiar with it. So, in string theory, we start with free strings, which are objects which are one-dimensional, infinitely thin, with a tension. Tension is a parameter, sometimes written this way, where this is called the string length for a reason we're going to see later. Now, these strings are relativistic objects. They have a tension which is equal to the mass per unit length. So typically, a violin string, for example, would have a mass per unit length which is much bigger than the tension. Okay, this is in units where c is equal to 1. Okay, and this implies, so this fact, this equality implies that excitations along a stretched string travel at the speed of light, and also that the string is pushed invariant along the direction of the string. So we can form closed strings as any object. They can oscillate, and we can separate these oscillations in normal modes, and we'll have quantized energy levels, and the mass of the object will be equal to the total energy contained in these oscillations. And so when it's not oscillating, it's oscillating in the ground state. We put all these normal modes in the ground state, we end up with something that turns out has mass equal to 0, and the first massive string state has a mass square which is for the tension. And the typical size of these objects when they are oscillating, or even for the m equal to 0 state, which is in the ground state, the typical size is given by 1 over the square root of the tension, or the string length. That's why it's called the string length. It's the typical size of the string. Now, these strings can interact, and they interact by touching and joining. And so in this way, we can write down these string theory Feynman diagrams. The simplest case is when they are moving in 10 dimensions and we have supersymmetry. And behind these pictures are precise mathematical formulas which give finite results for all these diagrams, and finite results to all orders in perturbation theory, as opposed to what happens in Einstein gravity. Now, although energy is smaller than the mass of the first massive string state, we end up with a gravity theory. So here we're imagining, so for spaces whose radius of curvature is much bigger than the intrinsic size of the string, we can approximate the string as being a point-like particle, and then gravity is a good approximation. So this is the main thing I wanted to say in these two transparencies. I wanted to say that so string theory is a kind of generalization of gravity, which has the virtue of being finite quantum mechanically, so it's a consistent theory, and that it reduces to gravity in long distances. How long do the distances need to be? Well, we need to have the radius of the space needs to be bigger than the size of the string. So that's the condition. So going back to the relationship, we have that this most supersymmetric version of QCD, or any course of Riemann theory, is related to string theory in ADS5 times S5. And we have this theory, we have an integer that specifies the theory, which is the number of colors. And here we have an integer, which is the magnetic flux to the S5, and these two are equal. Now here we have a sphere, for example, and we need to know how big this sphere is. So we need to know what's relevant is how big it is compared to the string length. And its size in string units, so in terms of the radius of the size of the string, is of order g squared n. And this is the coupling constant of the Young-Mills theory, and n is the number of colors. So that's the size you can calculate by solving essentially some equations, some gravity equations similar to the Einstein's equations with the magnetic field. And we get this one. Now, the important thing to realize here is the following: that when g squared n is small, the radius is much smaller than the string length, and in that case, the radius of the sphere, or the size of the space, is smaller than the size of the string. And in that situation, then gravity is not a good approximation to string theory. I mean, string theory is still well defined, but gravity is not a good approximation to string theory. And that's when we can easily do calculations here. On the other hand, when chi square n is large, then gravity will be a good approximation because the size is much bigger than the size of the space is much bigger than the intrinsic size of the string. But perturbation theory here will be very difficult. I mean, you cannot use perturbation theory when lambda is much bigger than 1. But this field theory is still well defined, and what you could, in principle, calculate it perhaps using the lattice and so on, but it is not easy. And so for this reason it's called a duality, because when one side is easy to analyze, the other side is difficult, and vice versa. And dualities are useful because they transform complicated problems into simple problems. So for example, if you assume that this is true, then a complicated problem on this side, which is a problem of strongly coupled gluons, a many-body problem with strong coupling, gets transformed into a simple problem on this side, into just a problem in classical gravity. So a highly quantum problem on this side gets transformed into a simple classical problem on this side. Okay, but of course the fact that it's a duality also makes it harder to prove, because if you wanted to or disprove, I mean, if you wanted to disprove this relationship, you have to compute something here and here at the same value of the coupling. But by now, there are many calculations that have been done and have tested this relationship. But one general lesson that we understand from here also is that these strings made with gluons on this side, so these are these necklaces that we discussed before, are becoming the same as the fundamental strings that we use to describe quantum gravity, but on a curved spacetime. So one thing that is, well, this is a picture that Alexander also showed in his introduction. So the radial direction, this is the radial direction of ideas, and its origin can be understood as follows. So when we have a massive theory, so we have a massive particle, in order to specify the state of the massive particle, we need to specify its 3 positions. And the massive particle is the simplest excitation of a massive theory. Now, if we have a scaling invariant theory, then the simplest excitation is some kind of blob that has a certain size. It could be this red blob, for example. And as before, we need to specify its position, but we also need to give it size. Okay? Since the theory is scale invariant, there are many other blobs that are related to the red blob by scale transformations. For example, this blue one here, they only differ by the action of a scale transformation. So the 5th dimension can be viewed as a geometric realization of this size parameter, so that blobs with different sizes correspond to particles in 5 dimensions that are at different positions along the radial direction. And this that I've set here with pictures can be precisely understood in terms of representations of the conformal group. So it has a precise mathematical representation. The phi sphere is related to the fact that the theory had 6 scalar fields, etc. Now we have a quark and an anti-quark on the field theory side, an external quark and anti-quark. We can separate them by a distance L in the boundary theory, and they will be joined by a string. This is the same string that we were discussing in the very beginning, except that it should be viewed as moving in the 5th dimension. So the fact that it moves in the 5th dimension is related to the fact that the string will have some thickness and will spread. And the potential is still given by the length of the string, but not the length of the string in the boundary theory, but the length of the string in the curved spacetime that we have here. And when you go and compute what this length is in the case of anti-de Sitter space, and this string is in anti-de Sitter space, you find that the potential goes like 1 over L, where L is the distance of the boundary. And this has the correct form for a scaling invariant theory, and you can calculate the dependence on the coupling, and it has this particular dependence, while the weak coupling result, this is essentially Coulomb's law, is proportional to G squared n. And of course, as we vary the coupling between, and this is a result that is valid at weak coupling, this is a result that is valid at strong coupling, and in principle there is some way of interpolating between these two, and only recently we developed techniques to actually in principle compute this interpolation, though it hasn't been yet fully computed. But there are at least some equations which if you solve you could compute that full function. Now so far I discussed the scaling invariant theories, but there is no problem in discussing confining theories. So in fact we can take this n equal to 4 super-Young-Mills theory and add masses to the scalars and fermions in such a way that we get the pure Young-Mills theory of low energies. And if you take the coupling to be strong throughout at all energies, then the gravity solution will be a good description. And then what happens is that the gravitational potential has the form that I discussed in the beginning. So it doesn't decrease forever as it does for scaling invariant theories, but it decreases and then it increases again. And you get this by solving these 10-dimensional Einstein equations in the presence of some perturbations here that are related to these masses. So you get this particular gravitational potential, and it has the feature that it has a minimum. So if you put a particle here, you would want to sit here at the minimum. That means that it wants to have a specific size. So, for example, this is analogous to what happens with the proton, where the proton is a bunch of excitations in the gauge theory, and it has a given size. You could make it smaller if you wanted. That making it smaller would be moving it in this direction. But here, that's the given size. And similarly, if you were to put a string, and you stretch the string along some direction, let's say perpendicular to the screen, then the string also will want to minimize its tension by sitting at this position. And then it again, from the boundary theory, would correspond to the fact that the string would have a finite width, and we recover the picture we said in the very beginning for the confining string. Now this is not confining QCD, it's not just pure QCD, this is a version of QCD with a strong coupling, a very strong coupling. Now so far I've said that I've given different ways of computing observables that have to do with field theories, but since this is a relationship that relates gravity to field theory, we can ask what we can learn about gravity from the field theory. The lessons that are most interesting is there are lessons for quantum aspects of black holes. So I remind you a little bit about black holes. So you know that gravitational collapse leads to black holes, and classically nothing can escape once you cross the event horizon. But quantum mechanics implies that black holes emit thermal radiations, and black holes, well, you have the paradoxical situation that black holes can actually be white. So if black hole gets smaller, it gets hotter, and if it is really small, it can be white. So a black hole of the mass of a continent is very small, the size of the wavelength of white light, and if you actually looked at it, it would really look white. It would not emit lots of light, it's about 1 milliwatt, but you would still be able to see it. Now this is a theoretical prediction, it hasn't been observed, but it can be obtained from many different points of view, and it's a prediction of combining quantum mechanics in the presence of black holes. The temperature is proportional to 1 over the size of the horizon, so that's the wavelength of the emitted radiation, and it's very tiny for black holes that are produced by natural processes, like astrophysical black holes, and well, it hasn't been measured. But it implies that black holes evaporate, and big black holes, like the mass of the sun, take a huge amount of time to evaporate. So a black hole, the thing to remember is a black hole of the mass of the mountain will take the age of the universe to evaporate. We don't know whether the early universe produced such black holes, but we don't know if that none of them have been observed yet. Now, but one interesting consequence of this is that the temperature, as usual temperature is related to entropy, and by using the first law of thermodynamics, we can calculate the entropy, and the entropy is the area of the horizon in blank units. So for a macroscopic black hole, this is a huge entropy, and the question is, what is the statistical interpretation of this entropy? So when a condensed matter physicist measures some specific heat in the lab and so on, and finds the entropy of the system, he would want to know what the statistical interpretation of that entropy is. And what is moving in the system that gives rise to the entropy? Or what are the states we are summing over to get the entropy? So here the idea is we can consider black holes in anti-de Sitter space. So now we change, it's not anti-de Sitter space anymore, it's really a space which is topologically different. It has a black hole in the middle. Near the boundary it is the same. And this will have some temperature, so it will be like taking this bulk space and putting it at finite temperature. And again we have some entropy, which is the area of the horizon. Now from the field theory point of view, it corresponds to a gas of gluons, or a fluid of gluons, which is again at finite temperature, the same temperature as the temperature of the black hole. And these gluons are interacting with each other. And in the field theory, the entropy could be calculated as the number of states. And in the cases where you can actually calculate this entropy is difficult to calculate in the boundary theory because these gluons are strongly interacting, but there are some special two-dimensional field theories for which you can actually calculate it. And in those cases, you see that there is a precise match between the entropy calculated from the statistical formula, such as this one, agrees with the entropy given in terms of the area of the horizon. So that at least gives an explanation for the entropy. And well, this also shows that you can use this to understand strongly coupled field theory. So if you had a system that has strong coupling, such as this strongly coupled gluons, you can calculate its free energy using this geometric description, which is the black hole description, which is much simpler. Now the evolution of another implication is that the evolution is unitary. Am I over time? No. The evolution is unitary, and so we know that black holes then are consistent with quantum mechanics. We don't know precisely the mechanism, but if you assume that the duality is true, then black holes should be consistent with quantum mechanics. There's also a nice relationship between the confinement, deconfinement transition in gauge theories and black holes. So we saw that the confining theories have a gravitational potential which is of this kind, and they have this field spectrum and so on. But if you start raising the temperature and introducing excitations here, if you raise the temperature by too much, then you find that these excitations here can produce a black hole, and you have a new phase where the gravitational potential really is going to zero here, signaling the presence of a horizon in the extra dimension. So the deconfined phase of gauge theories, or the quark-gluon plasma, in this picture is related to a black hole. So and this has been used to model high energy collisions. So in these theories that have gravity duals, if you have a collision between two particles, let's say two here, or two objects that are here localized in the extra dimension, near is equal to 0, as I told you they would be. So they would collide, and in the bulk they will produce a black hole. And we can understand this black hole from the field theory point of view as a droplet of the deconfined phase. So, for example, in the heavy ion collisions that are done in Brookhaven or the LHC, you produce this quark-gluon plasma, and in this picture it can be represented as a black hole which is localized in the spatial directions and sits at some point in the radial directions. And using this black hole picture, you can calculate the properties of, you can understand what's going on after this collision is produced. And in particular, these black holes behave as a fluid and have, and in fact you can as a fluid with a viscosity which you can calculate by solving Einstein's equations. Viscosity is the rate of dissipation, and in the context of the black hole is the rate at which waves that are near the black hole horizon fall into the black hole horizon. So that's something you can calculate using Einstein's equations, and in that way you can calculate the viscosity, and you get a very low value for the shear viscosity, and it's somewhat similar to the ones that are observed at the heavy ion experiments and read frequently at this. So this is a very rough model because we don't know the precise string theory corresponding to QCD. So here, what is done to do these calculations is to do these calculations not in QCD but in another theory that has gravity to it. So that's one of these applications. Now we said that we had gravity in the interior. Now we have gravity in nature, and suppose that we lived in anti-de Sitter space. Our universe is not close to anti-de Sitter, it's closer to de Sitter. But just for the sake of the argument, let's say that it was anti-de Sitter at very long distances. Then the ultimate description of the universe would be, which our universe is 4-dimensional, so it would be in terms of a theory which has the 1 dimension less, that lives at the boundary of the space, scaling invariant theory. And it would have to have a huge number of fields, of order 10 to the 120, that comes from the size of the universe, of our universe in Planck units. And so this would be the ultimate description of the universe if we lived in anti-de Sitter space. Now we don't live, as I said, in anti-de Sitter, but near, closer to de Sitter, and we can wonder whether we could have a similar description for the de Sitter case. And people have been exploring this description for the case of de Sitter, but we don't really understand it very clearly yet. So there are some proposals, especially for higher spin gravity theories, of a possible description using conformal field theory, but we don't yet understand whether it can be extended to any other case. So in conclusion, we should get from here is that gravity and particle physics, or gravity and quantum field theory, are unified. So the usual road to unification was that quantum gravity is somehow more fundamental, and particle physics can be derived from this more fundamental quantum gravity description. But what we're talking about here is that particle physics and quantum gravity could be equivalent in these situations, especially for some configurations of quantum gravity could be totally equivalent to particle physics. And this equivalence can be useful both for learning about particle physics and also for learning about gravity. We saw how black holes and the deconfined phase of gauge theories are related. And in this picture, space-time, especially one of the dimensions of space, is emergent. So it wasn't there in the beginning of the description, but was there at the end. So that's the radial direction of the anti-de Sitter space. So we started from a theory without gravity, and we got the higher dimensional field theory with gravity. And this could be a general feature of quantum gravity, that the fundamental description of quantum gravity could be in terms of some description where space-time is not part of the description. Space-time emerges from the description. So this is a tool for doing computations in gauge theory and a source of inspiration for condensed matter physics. And here in condensed matter is usually used to model the strong interactions. So you have a system in condensed matter where the constituents are strongly interacting, and you have described by some quantum field theory with strong interactions. You can model it by using these gravity constructions, and you can learn some things about it. It has to be used with care and understanding the proper relationship between the two theories, but it's been explored a lot now. And finally, it's also a tool to understand these conceptual problems in gravity, like black hole entropy and black hole dynamics. And finally, in the future, I guess people are trying to find theories closer. So if you're interested, so there are two general applications of this. One is applications to field theory. So one could try to find theories closer to the theory of strong interactions, that is to say, it's all largely QCD, or to apply it to condensed matter physics problems And for that, you try to realize constructions that have the various features and symmetries of the condensator physics problem you are interested in. And in gravity, if you're interested in gravity, then you would like the most interesting extension is to understand gravity in other spacetimes. Of course, we already mentioned some of them, for example, the ones that were due at non-confined interiors. But in general, you would like the most interesting problem is to understand cosmological spacetimes, and in particular, understand cosmological singularities. And hopefully this will lead to some way of doing this. Thank you.
I would like to thank you for the beautiful talk, and let us congratulate Juan Maldasena for the prize once again.